Please welcome Henry Zhong for a session entitled RecoNIC, RDMA-enabled compute offloading on an FPGA-based SmartNIC. Henry is a senior member of the technical staff in AMD and serves on the technical program committee of several leading conferences. Henry?
Thanks for the introduction. Let me share my screen.
We can see your notes slide. There it is.
Can you see the screen?
Yeah, it's perfect. Thank you. In presentation mode, yes.
Okay, good. Okay, thanks for the introduction. I'm Guanwen Zhong. You can call me Henry. I'm a senior researcher from the AMD Research and Advanced Development based in Singapore. So today I'm going to share one of the open source projects in our lab, RecoNIC, which is 100 gigabits FPGA-based SmartNIC with the RDMA and compute offloading. Let me first give you the background of this project. This right figure shows the chance of machine learning model size and AMD GPU performance over the past 10 years. And orange line is the trend of a machine learning model size, while the blue line is the AMD GPU performance. We are using the FP32 as the performance metric. So as you can see from this figure, the machine model size has increased about 8,600 times over the past 10 years. While for the AMD GPU performance, only achieve about 50 times improvement, which is also a very good number. But apparently, machine learning model size has significantly outpaced the growth in single GPU performance over the past 10 years. And now let's look at the Ethernet speed. So how it looks like. So in the right side figure is taken from the Ethernet roadmap 2023 from the Ethernet Alliance. Around 2010, they released a specification for the 40 Gbps and 100 Gbps specification, and around 2018 or 2019 they released 200 gigabits per second and 400 gigabits per second specification. So as we can see that over the past 10 years, the Ethernet speed is just improved about 10 times, which means that this is significantly slower than the GPU advancement, which is a 50 times improvement, and machine learning model size growth, which is 8,000 times improvement. So this led to the emergence of a scale-out architecture, which means that we will have a sea of a heterogeneous node connected via the high-speed network. And the right figure shows the one of scale-out architecture with a sea of nodes connected via the high-speed and low latency network interconnect. And for each node is a heterogeneous node. Includes CPU, GPU, FPGA, ASIC, such as a TPU and SmartNIC. So SmartNIC here will act as an intermediate hub for various components. And it can use to perform the regular NIC function. It can use to perform the value editing function, for example, the transport layer offloading engine, RDMA offloading engine, telemetry sensing. And also can perform the other layer processing, the transport layer and above. For example, the application layer, header processing, and it can use also integrate the accelerator inside the SmartNIC to do the streaming and lower-side computation. And for the high-speed and low-latency networking interconnect, generally they will use the RDMA, which is the dominant kind of a protocol in the high-performance computing and machine learning. And let's talk about the data communication in this scale-out setup. So in a traditional way, generally, if we want to copy the data from the local host memory to the remote, either host memory or device memory, we need to go through the PCIe kind of data copy. And if we want to copy the data in local device memory, to the remote kind of a device memory, we need to first copy the data to the host memory about the PCIe, and then use the NIC to copy this data to the other host memory, remote host memory, and then once it received, then the CPU will copy this data in the remote host memory over the PCIe to the FPGA device memory. So you can see that there is multiple kind of a data copy involved over the PCIe. But if we have the FPGA-based one, then we can let the FPGA to directly take this data from the host memory or device memory, and then transfer to the remote host memory as a remote device memory. And if we have an FPGA attached to the PCIe switch, for example, like this one, then if we want to write the data to this device memory, we can let the FPGA to directly write the data to the device memory over the PCIe peer-to-peer communication protocol. So I mean, with the FPGA SmartNIC, we can enable the direct memory access among peers, and since we are using FPGA, right, so we can have our accelerator inside the FPGA so that we can bring the network data as close to the compute as possible. And what kind of a programmable smart feature do we need to scale off this? The first thing we need is we need to support the normal network packet in the SmartNIC, for example, TCP, UDP. The second thing is that we need to support the RDMA traffic. This RDMA engine should be shared by the host, should be shared by the host, GPU, FPGA, and other ASIC components. And since we are using FPGA, so we can let the FPGA SmartNIC to do the streaming or load aside compute acceleration, so that we can bring the network data as close to the accelerator as possible to lower the latency and improve the throughput. And why we need the RecoNIC? First reason is that RDMA is the dominant kind of a protocol for the machine learning and HPC application, so it's very important in this domain. And second reason is that the existing FPGA-based SmartNIC, for example, the OpenNIC from our team and the Groundle from the UCSD, they are just a basic SmartNIC. They don't have any kind of transport layer offloading engine inside. And for other kind of transport layer offloading engine, for example, the Microsoft Catapult lightweight transport layer engine, they are not the RDMA engine. And the TCP offloading engine and the RDMA offloading engine from the ETH switch, and also the AMD's YARNIC IP, it's not integrated inside the a proper FPGA-based SmartNIC, and it's not. So at the moment, there's no open source RDMA-enabled FPGA-based SmartNIC platform available. So that's why we bring the RecoNIC onto the table. RecoNIC is an open source 100 gigabits FPGA-based SmartNIC infrastructural testbed with the RDMA and compute offloading, and it can use to enable the scale-out heterogeneous system, and it can enable the direct memory access among the network connected peer, and it can also bring the network data as close to the hardware accelerator as possible. This figure shows the RecoNIC system architecture. It consists the hardware component and the software component. In the hardware shell, we have the RDMA engine, and we have the load-aside compute box and the streaming compute box for the acceleration, and we have the packet classification module to identify whether the incoming traffic is RDMA traffic or not RDMA traffic. And then we also have a MAC subsystem and the QDMA subsystem, and memory controller and arbiter. For the software stack, we have a network stack to handling the non-RDMA traffic and RDMA traffic. And the memory driver is used for the data communication between the host memory and the device memory. And the control driver is used for the register configuration and the compute configuration to the lower side compute. Let me give a few examples to show how the RecoNIC work with these things. So first example is show the non-RDMA traffic. So for the non-RDMA traffic, we leverage the software network stack to deal with it. So the software network step first, we prepare the packet and then send over the QDMA subsystem all the way to the TX path of the max subsystem. And similarly, for the IX path, we will receive it from the IX path of the max subsystem, go through the packet classification. Since it's a non-RDMA traffic, so it will redirect to the QDMA subsystem all the way to the IX path of the network stack. And for the RDMA traffic, I will use the RDMA write for the TX path example, and then using the RDMA read response as the IX path example. So in the RDMA, we will have the queue pair, and queue pair is kind of data structure consists of send queue, receive queue, and completion queue. Send queue will consist multiple kind of work queue element, which we call it work key. It's kind of a data structure which detected by the RDMA engine to perform the corresponding RDMA operations. And then completion queue is used to store the completion queue element to indicate when the RDMA operation is finished. And then the RQ is used to store the data for the RDMA send and receive operation. And user buffer is kind of data buffer. We store the where we keep the payload. So for the RDMA and this queue pair and the user buffer can either be declared in the host DDR or FPGA device memory in the RecoNIC, which is very flexible. So for the RDMA write example, the first thing we need to do is at the host side, we need to declare the queue pair and construct the work key, and then write to the send queue and update the and also configure the RDMA engine and update the send queue doorbell. Once the RDMA engine detect or aware this send queue doorbell update, they know that there is an engine in the send queue. So they will fetch this work key from the send queue. And based on the work key, they will fetch the payload from the user buffer and construct the RDMA write packet, and then send it over to the TX path of the max system, and then wait for the remote peer to send us a write. To send us a RDMA write acknowledgement packet. And the RDMA engine will validate this RDMA write acknowledgement packet. If it's the valid kind of acknowledgement packet, then I will update the send queue, update the completion queue with the completion queue element, and also update the completion queue doorbell. And at the CPU side, they will pull this CPU doorbell to detect when the RDMA write is complete or not. That's the text part of the RDMA write. For the IX path, we are using RDMA response. So the first thing is the remote side will send the RDMA request to our local node, and then our local node will create an RDMA response and send it back to the remote node. So the first thing we need to do is to declare the memory region in our host memory, and update this information in our RDMA engine. And of course, need to share some of the information, for example, the security key of this memory region and the remote and the base address of this memory region to the remote peer. So all this operation is done by the handshaking stage. So and then the RDMA engine will wait for the RDMA request from the remote peer, from the IX path of the max system, and then the RDMA engine will validate this RDMA request whether it's a proper one, and then if it's a proper one, then it will fetch the payload and construct an RDMA response packet, and then send over the TX path of the max system. Yeah, that's the IX path of RDMA response. And similarly for the queue pair and the use buffer, this memory region can be declared either in the host DDR or device DDR. And in RecoNIC, we have two compute box. One is a lower side, the other is a streaming. So lower side compute box is used for the compute acceleration over the data store in the device memory. For example, the metric modification. We need to wait for array A and array B and do the computation right to array C. It's not a streaming mode. We can't, do this thing in library or do in network kind of a measurement. We have to wait for the data. So this lower side compute is for such kind of application. So the right side shows the architecture of the lower side compute. So for each kernel, we will have a 2 fiber attached to it. So one is the control fiber, the other is status fiber. So control fiber will contain the compute control command. So compute control command is similar to the C code when we call a function. We will give the argument to it, and this argument actually is the compute control command. And it can construct by either CPU or FPGA. So the CPU or FPGA can write this compute control command and push to the control fiber, and the kernel will detect whether there is an element inside the fiber. If yes, then they will take the elements from the control fiber and then going to read the data or roll the data from the memory and do the computation. And once done, they will update the complete information into the status fiber. So either the CPU or the FPGA logic can pull this status fiber to be aware whether the completion is finished for a specific task. And this kernel can be written in a C, and then using our high-level synthesis tool to convert the C into the RTL. And also user can directly write the RTL to design this hardware accelerator. For the streaming compute, it's used to do the compute acceleration over the network data at run rate. So potential use case could be the packet processing application. For example, the packet classification, forwarding, checksum offloading, upper layer processing, telemetry, or line rate application processing. For example, the in-network aggregation. We can all push to the streaming compute boxes. And you can see on the right side architecture is very simple. The interfacing is just a streaming in and streaming out. And then we will have a configure interface to configure the register inside the streaming compute. And the user can write the P4 or the C code, and then using the YTS networking P4 to convert the P4 into the RTL, or using HL's high-level synthesis tools to convert the C code or C into the RTL. Or user can directly write the RTL to design the hardware accelerator in these streaming compute boxes. Regarding software, RecoNIC software stack, the networking stack, we have two parts. One is a non-RDMA traffic. The other is the RDMA traffic. So for non-RDMA traffic, we will go through the ONIC driver, which is kind of a standard software network stack integrated inside our OpenNIC shell. And to deal with the traffic like TCP, UDP, such kind of RDMA traffic. And for RDMA traffic, we will have a two set. So one set is the kernel bypassing RDMA API, we call it RecoNIC. And in this RecoNIC application can directly call this API and communicate with our RecoNIC hardware shell to send and receive this RDMA traffic. And the other set is goes through the RDMA core. So we have a Reco provider integrate inside the provider system of RDMA core, and then connected to a RecoIB, which is a kernel space driver. And RecoIB will be communicated with our hardware RDMA IP. And for the memory driver is used to used for the data communication host and FPGA. So in FPGA memory, and in this case, the host will act as a master, and the control driver is used to configure the register inside hardware, and also the construct the compute command and pull in the compute status. For the lower side compute accelerators. And in the RecoNIC, we provide two examples. One is a lower side example, the other is a streaming example. For the lower side example, we use the metronome application, and we assume that the data is stored in a tier 1, and the compute is done at tier 2. And this left side shows the compute control command, how it looks like. So it contains the base address of array A, B, and C, and the dimension of array A and B, and the work ID to identify which task. So the right side shows the workflow of this example. The first step is to do the initialization and handshaking to get, for example, the remote address of array A and B and security key and some of the packet sequence number to set up the RDMA kind of a connection. And once we get all this information, we will construct the work key for getting array A's data and array B's data and ring the secure doorbell. In the RecoNIC RDMA engine, will detect this kind of doorbell update. Then they will fetch this work key and construct a read request and send it to the remote peer. And remote peer see this read request, will prepare this array response packet and send it over to the peer 2. And peer 2 receive this RDMA response. They will write this payload into either device memory or host memory, and then let the CPU know that all the data is ready. And then the CPU will generate and issue a compute control command to the accelerator. And then the accelerator will take this compute control command, load the data from the memory, and then do the computation and write back to the memory and signal the CPU that all the computation has been done. So as you can see that in this example, we still let the CPU to pull, for example, pulling the CQ doorbell and wait for the compute completion. So CPU is still in the critical path and still waiting some of the CPU cycles. And we have another kind of example which try to let the RecoNIC, let the FPGA logic to handle all these kind of CPU control operations, so that we can remove the CPU out of this critical path. And in this kind of example, we can lower the latency. And for the streaming example, we use the packet classification. And packet classification is used to identify whether the incoming packet is RDMA or non-RDMA traffic. So the right side shows the P4 program, which contains the parser and forward parser instance, forward instance, and the parser. So the parser instance is basically the final state machine. Pass different kind of a header of the incoming packet. And then the forward instance is try to fill the metadata information. And with this kind of P4 program, we send it to the wireless networking P4 and generate an RTL. And then we integrate this RTL into our streaming compute boxes. And the import of this streaming compute boxes is basically just a AXI4 stream interface. And regarding the leaf fabric, so at the moment, the current software and hardware system of the RecoNIC have 3 parts. So we have a only driver for the non-RDMA traffic, which deal with the TCP or UDP. And then we have the RDMA traffic either using the kernel bypassing mode with the RecoNIC or the standard RDMA API through the RDMA core over the Reco provider or Reco IB all the way to the RecoNIC shell. And for the leaf fabric things, they provide, similar to the RDMA core, they provide a provider to communicate with the underneath driver, and including the TCP or verbs as the provider. So for the TCP, we can connect to the only driver, and for the verbs, we can directly connect to the RDMA core, since the RDMA core provides the leaf ID verbs, and it use the similar kind of, it use exactly the same API, the RDMA API. So with this kind of integration, we can actually let the leaf fabric to go through the verbs and all the way to the RDMA core and Reco provider and Reco IB, and communicate with and use or communicate with the RecoNIC shell. And the user writing the application can directly connect that application using the leaf fabric API. So that's one of the possible integration to build the leaf fabric over the RecoNIC. Yeah, let's share some of the performance number for the RecoNIC. So this slide shows the data movement performance. We are using the host as a master in this slide. So the host will trigger this memory access over the QDM AXI memory map channel. So regarding the bandwidth, for both read and write, we can achieve 13 gigabytes per second for transmitting data over the 512K byte data. And we are using the PCIe Gen 3 x16, which means that 13 gigabytes per second is almost the peak practical throughput for it. Regarding for the latency from the host to the device memory, it's slightly high, about 22 microseconds for small message. This is because of the driver side. We need to do a lot of register configuration, so it brings a lot of overhead to the small message. So that's the reason. So this is the data movement with the host as a master. So if we use the FPGA as a master to access the host memory, then the latency will be much slower, much lower. So in this slide, I show the FPGA as a master to access the host memory or the PCIe bridge. So as you can see, if we transfer 64-byte data, the write latency is just a 0.17 microsecond. For the read latency is just a 0.62 microsecond. So in this figure, the blue line and the orange line shows the PCIe bridge read and write kind of a latency. You can see it's much lower than the host as a master for this data movement. And similarly, we also plot the data for the FPGA to access the device DDR. And it can achieve a lower latency compared to the FPGA as a master to access the host memory. And as shown in this figure, the purple line and the green line. For the write operation, we can achieve about 96 nanoseconds, and the read we can achieve about 196 nanoseconds for transmitting 64-byte data. So the access latency to the device memory is lower than that in the host memory from the FPGA. And for the RDMA read performance, in this example, we are using the queue pair defined in the host memory. So all the walk keys stored in the host memory. FPGA need to FPGA DDR, FPGA RDMA engine need to load the walk keys from the host memory. And we first talk about the RDMA read latency. The control on CPU and control on FPGA means that so the control is RDMA control. For example, the thank you doorbell ringing and completion doorbell calling, and all these operation we either push onto the CPU or push onto the FPGA. So of course, I mean from this figure we can see that if we push all this control onto the FPGA, then we don't need to go through the PCIe to configure this register, and our latency can achieve lower compared to that on the CPU. And for that control on the FPGA, we can achieve around 3 microseconds for the smaller message, while for control on the CPU, it achieve around 4 microseconds. And if you talk about the throughput, the single request here, the single request and the batch request here means that for the single request, we measure the performance like that. We first create the walk key, start the doorbell, ringing the thank you, start the timer, ring the thank you doorbell, and wait for the completion doorbell, and end the timer, and get the difference between the end timer and the start timer, and do it multiple iterations to get the average number. And for the batch mode is that we will create a batch size of walk key in the thank you, and then we start the timer. We update the we ring the thank you doorbell once, and then wait for all the completion queue to be completed, and then we end the timer, and then we get the difference between the end timer and the start timer, and then we do it multiple iterations to get the average number. So as you can see that the batch mode and compare with the single mode, the batch mode has a less kind of a PCIe access, so which means that we will have a better performance, which is also shown in this figure. So compared to the single request, which is shown in the blue line and the yellow line, the batch request, the green line and the orange line can have a much higher throughput. And compared with the control on the FPGA and control on the CPU, we push the control on the FPGA can have a better throughput compared to control on the CPU. And both batch requests on CPU or FPGA can achieve the near line throughput. with the RecoNIC. And for RDMA, right, we have the similar kind of behavior. And previous one, we have the Q pair declared in the host memory. And what if we declare the Q pair in the device memory? So the right side figure shows the RDMA write latency and RDMA read latency with the Q pair declared in the host memory and device memory. So we can see that the orange line, which is the Q pair declared in the device memory, has a lower latency compared to the Q pair declared in the host memory. So the reason is that FPGA as a master to access the device memory has a lower latency compared to FPGA access host memory or PCIe, and it's around 100 kind of a cycle. We can save around 100 cycle, 100 plus cycle, and since the FPGA is running at 250 megahertz, which is a 4 nanosecond, it's around 500 nanosecond to 600 nanosecond kind of range. Yeah, and the RDMA latency share the similar behavior. And regarding the RDMA throughput, either for the Q pair declared in the host memory or device memory, we share the similar behavior. Both can achieve the line rate. Yeah, in conclusion, RecoNIC is an open source smart infrastructure and testbed for scale-out computing. And RecoNIC is the first smart platform interfacing with the AMD enabled with x86 CPUs. And it provides 100 gigabits per second line rate RDMA traffic with low latency. And it also supports the streaming and local site acceleration while the wireless networking P4, while JAWS or RTL to process the network data. And RecoNIC is available in our Science GitHub repository. And we also have one final paper published in the archive for the RecoNIC. And if you are interested in the RecoNIC, please reach out to me. Yeah, that's all for my today's presentation. Thanks a lot.
Cool. Thank you. So we're in just a couple minutes over, but do we have any questions for Henry? Nick, your question.
Yeah. So a great talk, by the way. Can you show that IB verb slide again real quick?
Yeah. This one.
Yes. So in this, so you're basically saying for future work there might be a libfabrics API provided, but is there are there functionalities in the Reco IB or like the Reco provider that sort of provide functionality that the libfabric API would not provide?
So I haven't looked into the detail of the verbs provided in the libfabric. And I'm not sure whether there are some extra kind of API which is not related to the standard RDMA core kind of thing. But at the moment, the standard RDMA core API is directly connects through the record provider and all the way to the record IB's driver and configure the RecoNIC shell. So for example, register the MR. So we use the IB rec MR, right? IBV rec MR, and also IBV create Q pair, and all this function is directly connect to the record provider, and then inside the record provider we will have this kind of processing and then connect it to the record ID. So if the verbs only contain this kind of standard API provided by the RDMA core, then I think can directly connect.
Okay, thank you.
Okay, and we had a question from Shen. What is the capability of RecoNIC? How many Q pairs can it support with device control?
It depends on the RDMA engine we have. So at the moment, there are two versions RDMA IP provided by the AMD, and one version is RecoNIC 3.1, which only support 256 Q pair. And for the other RecoNIC 4.0, which can support up to 2048 Q pairs. Yeah, so it highly depends on the RDMA IP provided by the AMD. And I'm not developing that IP. I'm just use the IP.
Cool. Thank you, Henry.